in this video, we're going to go through some foundations of artificial intelligence. What exactly do we mean by that? We are going to discuss some disciplines, some research areas or subject areas other than, let's say, computer science, of which we are an integral part, how they have contributed to the evolution and the construction of and formalization, formation of thoughts, intelligence, as well as artificial intelligence. So, ideas, viewpoints, techniques that have contributed to AI in general. Several people have contributed, there's no doubt about that. However, when we look at the historical perspective, we are forced to kind of concentrate on a small number of people or subject areas, and perhaps not mention those that might have contributed. Yet we don't have time to actually go through each one of them. The history in general of AI is actually based around a number of let's say questions or queries, okay, that people have been looking at from various perspectives since ages. And this thought process actually has been on for at least 2000 years, more than that. And that's a very interesting note. However, modern computing is only, let's say, less than half a century old. So this gives you the relative time perspective in terms of how old the thought, the approach, understanding of philosophers in general and other people have been towards the working of the mind. And this is one of the most intriguing part of all scientific development. The question that we are going to refer to are not exhaustive. They just give you a flavor of what people thought they were trying to answer. And in trying to answer those questions, they led to some new discoveries, ideas that actually were picked up by other disciplines, including AI. And also making intelligent machines or artificial intelligence as such. Now, medical science is not interested in making intelligent machines in general. They are trying to understand the behavior of the mind, how it works, how it thinks, how it processes information, as we'll see later on. But along the way, disciplines such as ours have actually obtained a lot of new information, knowledge out of those. Okay, so number of these subjects include philosophy, mathematics, economics, neuroscience, computer science, engineering, linguistics, and so forth. So we'll try and go through each one of them a little bit and understand what they were trying to achieve by posing a few questions, and how they were resolved, and then what we learned out of them. So let's start with the philosophy. Philosophers thought ages ago that can we have formalized rules to draw valid conclusions. So if you have a certain amount of information, say for instance, in very common sense, if it is overcast, can you conclude that it's going to rain for sure? So these are those very valid basic questions, just to give you the idea that can we draw valid conclusions given a certain amount of basic information and knowledge that we have. So that's one of the things we're talking about. And then how do you relate the mind, as we call it, and the brain? So brain is a physical item. The mind in general relates to that, but we don't refer to mind as something which is physical, but the brain is. How do we correlate these two? Where does knowledge come from? Where is it stored? Where does it rest? How do we process knowledge, and how do we take decisions? So how does knowledge lead to action? First, we need to know where the knowledge comes from, and then how do we take decisions based on that. In general, then, the brain has been thought of as made up of two components: the logical side of the brain, and the other is not so logical, or metaphysical, so to speak. I didn't want to use this term, but just to explain. So a major portion of the brain is actually logical in its working. Okay, and this brings up a very interesting concept of logic, deduction, how to infer new information. Okay, so once we have some basic information knowledge, as I said about let's say the clouds and so forth, so can you deduce something? Can you infer new information out of it? Okay, this would be reasoning, and this is being done by the rational part of the mind. So for instance, if you know A is greater than B, and you also know that B is greater than C, A and B and C could be any physical concepts, mathematical concepts, then you can reasonably assume and infer and deduce that A will be greater than C. This is a kind of inferring new information from given certain information. Deduction, as we call it, deduce, infer new information. Other examples very common in philosophy. They say Socrates is a man and all men are mortal, therefore Socrates is mortal. So what are you doing here? You're taking some basic premises. Okay, he's a man, all men are mortal, therefore he is also a mortal. So what are you trying to do? You're trying to move logically from one point to the other. So Aristotle actually did a lot of work on this, and remember, this is more than 2000 years ago, and he formulated a precise set of rules to determine how the brain reasoning, the rational part of the brain, how that works. And he created something called syllogisms. Okay, example of what you saw earlier on. Okay, so using syllogisms, he was able to formulate rules that could determine, all right, if you have this, you can move forward, and this is how the brain is going to work. So you can generate conclusions given some basic information and knowledge. In fact, this went on to, and this was, as I said, about more than 2000 years ago, but the ideas were so firm and made sense that people actually built mechanical machines that could deduce new information, and mechanical calculators. They of course didn't come about until about 2000 years after Aristotle came out with these syllogisms, but it helped us with the understanding. So mechanical, so to speak, computers were actually built about 200 years ago, but of course they made logical conclusions, and they were actually correct. And then at the same time there were speculations, and the machines may not just conclude, they might be able to think on their own as well. So look at how the human beings, looking at the brain, the philosophers were actually thinking forward in terms of the ability of the brain, and the brain can act on their own. So if you want to believe that the pure physical brain, that's what it is and nothing else, then you might be able to say the brain doesn't have its own free will because everything is logic. Well, that exactly is not true. But physical mind, if we were to stick to that, somebody will say, all right, there's no free will. If it starts doing something, okay, it'll do it. But that is only a perception in terms of the choices available. Okay, so the brain does work the way we want it to. Then comes reasoning. Okay, and this is based on something called rationalism. Only believe something that is based on reason and can be proved. And Descartes was a very strong proponent of this philosophy, that in order to understand the working of the world, you need to understand the power of reasoning. Descartes also came up with the idea that there's the other side of the brain as well, okay, something called dualism, that yes, there's a physical part of the brain to which laws of physics apply, and there's another part of the brain to which these laws don't apply. So brain under laws of physics constitutes the mind. The physical mind manipulates knowledge that we have seen. The next problem is to establish the source of the knowledge. How do we get the knowledge? Okay, we have shown, demonstrated by the example, one example that we saw, that the brain can reason about things. But the point is, what is that? The reasoning is based on knowledge. Where is that knowledge coming from? What is the source of knowledge? And something called the principle of induction. The principle of induction has been formulated, which states that general rules are required by exposure to repeated experiences about something. Okay, repeated experiences. So when in real life we come across repeated experiences about any phenomena, physical or otherwise, we begin to take note of that, and the mind and the brain begins to reason that yes, if these things are happening, then we can generalize a few other things. So this generalization, called induction, okay, is a mechanism whereby the knowledge is being kind of processed. So specific instances happening a number of times leads to certain generalizations. On the other hand, deduction, this example of A greater than B and B greater than C, this is deduction, very precise things, right? But the fact that if it's overcast, it's going to rain, right? This inference, okay, this induction is a generalization, may not always be true, but very interesting in terms of comparisons. So in general, if you observe, all dogs like to eat bones. Now, nobody has given us this formula as such. What we've done is we've observed over a period of time, and we say, all right, yes, we know all dogs like to eat bones. Or if you observe long enough, this repeated experiences, monkeys, they like to eat bananas. So you can reasonably conclude that all monkeys will eat bananas. Given a bag full of, let's say, small boxes, you bring out one and look at the color. It appears to be, let's say, black. You open up another marble from there. It looks black again. You look at 3 or 4 other, samples, and all of them appear to be black to you. You reasonably conclude that this bag is full of black marbles. So this is generalization given a small set of observations. So we can say that all knowledge can be characterized by logical theories ultimately to observation sentences that correspond to sensory inputs. Well, what I'm saying is that all observations that you take are based on your sensory inputs. So everything backtracks to sensory inputs, the 5 senses, or as we call in Urdu, Hawas-e Khamsa. These become our sources of collecting the observations, and they come into the brain. Okay, so sensory inputs provide you some data based on which you make observations, and repeated observations, okay, lead to knowledge and interesting concepts. Coming back to the next one, mathematics as a science has also contributed, and some of the questions that the mathematicians wanted to know: are there any formal rules to draw valid conclusions, such as logic, for instance? Okay, and what can you compute? What is computable? What is not computable? And perhaps the third point, the mathematicians want to answer was processing fuzzy information, uncertain information. So these 3 things: formal rules to arrive at conclusions, valid conclusions, what is computable, and how to deal with incomplete or uncertain information. Remember, in general, every study, in order for it to be considered as science, requires three things: logic, computation, and probability. That's what maths is all about. One of the biggest contributors to this theory is George Boole, who came up with this propositional or Boolean algebra or Boolean logic. This is a formal logic whereby mathematics started to develop, very quickly. Things can have certain objects, certain concepts can have only two values: either it's true or false. A button is either on or off. It's 0 or 1. Okay, something is either true or false. This, in fact, such a strong and a powerful concept, is actually the very foundational basics on which the entire computing system is based. Yes, no, 0, 1, true, false, either or, and so forth. So this is how powerful that is. And as you can see, maths is a very strong basis on which all of our machines are built. Then, of course, what can we compute, what cannot be computed? And then there are limitations on deductions as well. What can you deduce logically and what you cannot deduce logically? Some functions, okay, it has been proved, can be proved, are very obvious, but they cannot be proved. So people came up with this concept that certain functions are called computable functions, which can be computed, which can be worked out. Certain others cannot be. And in there, Alan Turing, the man known for the Turing machine, he came up with these ideas, and he suggested that certain problems can be computed based on certain assumptions, and certain other problems, they can be so complicated that you can take infinite amount of time and still not come to a conclusion. There are other examples as well. Integers, for instance, we can't prove that all integers belonging to the set of natural numbers, 0, for instance, does not have a natural number coming before 0, but it's still a natural number. So this cannot be computed. Simple as that. So some problems actually are solvable, and others they are not solvable, not computable. That's what mathematics came about. And something called tractability, something that can be done, something cannot be. So if you've got a large problem to resolve, okay, then the only way to solve that problem would be to divide it into something which is doable and then add them up together. If you were to look at the entire problem, counting the number of stars in the world is impossible. You simply can't do it. If you were to do it, you might want to start with smaller solar systems and then increase them. You come to a larger subset and superset and so forth. So work on AI has helped explain why some instances, some problems remain doable, some are not. And that's where we come to the third part, which is uncertain reasoning. Probability is a concept introduced during prediction of the gambling events. During gambling events, people wanted to predict that if a dice is thrown, what is going to be the top face that comes up, and money was involved. And based on that, probability actually came into kind of existence and use. Let's move to economics. How has that contributed? Economics is, most people believe economics is about money. If you ask economists, they say, no, we don't deal in money. What we deal in is how do we make decisions to maximize the outcome of the decision that you've taken? And how do we do it when others don't agree with your choice of decisions? And how is it easy or difficult? And how do you come to decisions, the outcome of which is probably uncertain? You don't know when the result is going to be. It's not going to be immediate, it's going to take a long time. So these three questions they generated the idea of the decision theory. But before decision theory, one small little idea. Coming back to the decision making, for instance, a very common example typically given is McDonald's. It actually serves you a burger for, let's say, $1. They're hoping, McDonald's, they're hoping that you would be willing to exchange your dollar that you have in your pocket with the burger that they have over there. Now, their preference, McDonald's preference, is to get my dollar to them. And am I going to take that decision and pass on my dollar to them in exchange for the burger that they're trying to give me? So this is the economics that we're talking about. It's called the principal theory of utility and preferred outcomes. So the preferred outcome for McDonald's would be that I part with my dollar and I give it to them, and in return they give me that burger that they're trying to sell. So this is economics and decision theories. How to maximize the results of the outcome is what decision theories and operations research and so forth has come about. And then, of course, this has led to rational agents. So economics, operations research have contributed to rational agents, programs, human beings, and so forth, who take rational decisions, meaning decisions that do not involve emotions. They're based on reason only. Then one last thing within economics, something called satisficing. That's a term coined almost 50 years ago by someone called Herbert Simon, who got a Nobel in economics. He said that most human beings, if you were to model their decision-making process, you will see that human beings don't take decisions after careful consideration of each and every option that they have. They don't do it. They don't have time. They may not have resources. What they do is they take decisions based on something which is, so to speak, good enough, as long as most of the things that they're trying to ask for, designing a house, for instance, how many bedrooms, location, okay, the sizes, space utilization. They can go into infinite kind of combinations, and it might take 2 months for them to come up with the best solution. Instead of doing that, they come up with acceptable solutions within a reasonable period of time. And that's what Simon said, making decisions that are good enough human beings. And that is the understanding of the brain that we get here. Next one, neuroscience of brain. And that, ladies and gentlemen, once again has been a very, very kind of a watershed. The discovery of the working of the brain based on something called neuron, a cell that exists in the brain, and numerous millions and billions of them. Okay, these cells live in the brain and they are interconnected, and their interconnection actually processes the information. Okay, and this came about almost in the middle of the last century. Okay, and that has actually accelerated the growth of work in artificial intelligence. So how do brains process information? Based on the working of the neurons, and that has created these nerve cells, and which has led to the application area in AI as artificial neural networks, learning algorithms. We'll come to that later on. So that's neuroscience and brain. Psychology, of course. How do humans and animals think and act? Cognitive psychology uses brain as an information processing device. So, we learn from that. And they say that there are 3 key steps of a knowledge-based agent. We'll come to that. Stimulus must be translated into internal representation. Stimulus, remember, the 5 senses I mentioned, Havas-e Khamsa, that's your stimulus. It must be translated into some internal representation, what we typically call as conceptualization. That's the first part, okay? Representation. Then manipulation. That representation is manipulated by the cognitive, the processes within the brain, let's call it, okay? Keep it simple. And then these in turn are retranslated back into action. So sensory inputs coming in, represented in one form or the other, okay, processed and action taken. So this is kind of a summary of the steps that we've learned out of psychology. Finally, coming computer science and engineering, that's what we are, okay. Now, given all the contributing subject areas, okay, here we are now trying to make intelligent machines which are trying to copy, emulate, mimic the working of the human mind. And of course, the biggest thing that we need is the artifact on which this can be built, and that of course is computer. So from the hardware side, you need a computer, or from the software side, operating systems and programming languages and tools needed to program, so forth. So they have contributed to the working of artificial intelligence. So, ladies and gentlemen, this was a kind of a summary of what all disciplines have contributed to AI. I hope you find it interesting, and we'll see you next time. Thank you very much.